Thank you. Hello everyone, I am Jafarimoghaddam and I am working on advanced mathematical and computational optimal control with applications in aircraft trajectory optimization supervised by Professor Manuel. So first we start with introduction and which I have subdivided into three parts: motivation and the problem statement, well-posed mathematical approaches so far, and the research gaps. And then we move to the proposed methods. There we have proposed three different methods to just replenish the existing gaps in the literature. The first is optimal decomposition method, recently published, known as ODM. The other is perturbed analytic direct transcription for optimal control, known as PADUC, which is still under revision. Hopefully it will be published soon. And the other is indirect bank singular algorithm, that we call it IPSA. Okay. This is my motivation that comes from the lack of mathematical-based solutions for aircraft trajectory optimization, that this motivates me to go forward and to see what's missing there. So what is a trajectory optimization problem by itself? So this is a class of optimal control problem that can be formulated as you can see in here in a Mayer form. Here we have the objective function and subject to system dynamics and some inequality constraints and boundary conditions. These system dynamics and these boundary conditions are somewhat regarded as equality constraints as well. So here we are trying to just move these initial sets to the final sets by these control decision variables, so which are piecewise continuous variables that can just move the initial solution to the final solution. So the problem is to find these control vector. So here the well-posed mathematical approaches to solve optimal control problems or trajectory optimization problems are PMP, or Pontryagin maximum principle, which is the indirect method. This is something what we label it as. And the other is gradient-based parameter optimization method, which is known as direct approach. And the other is dynamic programming in approximate or classic form. Here we focus on indirect and direct methods. And we just skip from the dynamic programming part. So for the indirect method, conceptually the method dualizes the problem and then discretize them. The dualization is linked to the Hamiltonian, is linked to the co-state dynamics, which we use the partial derivative of Hamiltonian. And then discretization is based on maximum principle. But in direct method, we first discretize the problem to form nonlinear programming. The discretization can be based on different numerical methods or collocation methods, which are mainly trying to approximate this state deficiency function. So then we feed this nonlinear programming to an optimization module, which can be IPOPT, interior point solvers, or successive quadratic programming. And their optimization module is trying to solve these KKT conditions. So the research gaps, I have divided the research gaps into two parts: indirect method and direct method. For the indirect method, the research gaps can be highlighted as complexity in computing multipliers. The multipliers can be those from equality constraints and non-equality constraints, and lack of theory to identify the number of possible discontinuities, or the theories are actually non-existent. Lack of theory with regard to the continuity of the multipliers and the Hamiltonian functions in the problems with state inequality constraints. And the last is complexity in derivation of the singular controls and their interactions in the case of multiple singular controls. So for the direct methods, the gaps can be mentioned as highly sensitive to the initial guess or solution, especially when the problem is strongly nonlinear, chattering or fluctuating response over the singular extremals, which is due to the ill conditioning of the projected Hessian matrix. And the two main transcription methods, the first one, collocation based transcription methods, are analytic only at the collocation points, and they lead to more memory storage because the states are explicitly defined in terms of control variables. And the shooting-based transcription methods require high number of nodes. This usually ends up with a dense nonlinear programming. So the bad point is an aircraft trajectory optimization, or ATO, involves all the above issues. None of them here is relaxed. So the ultimate goal of my PhD thesis is to develop a special analytic-based algorithm to solve complex ATO problems. This is what we are aiming at. So as the first step to go towards this goal, we designed a new method known as optimal decomposition method, which is by itself a frontier analytical nonlinear solver that generates a unified solution over the whole domain. So the solution is in the perturbation form and in a series form that is based that is linked to an auxiliary linear operator. So we are not going through the mathematical details behind ODM, but just mention the advantage and the drawbacks of ODM and the reasons that we move toward the other method. So this ODM, the advantage is that in direct optimization, ODM can compute the multipliers with no shooting process. And this is something that happens when the ODM is applied to solve an optimal control problem formulated through the Pontryagin maximum principle. So no shooting process is required. And the drawbacks is that in indirect optimization, ODM cannot be easily adapted to the problems with singular or bang structures. And in direct optimization, the resulting NLP is essentially a dual objective function which restricts the application of the ODM. So for this reason, we moved toward an enhanced solver or an enhanced method that we name it as perturbed analytic direct transcription for optimal control, PADUC. The paper is still under revision, and we will hopefully have it published soon. So PADUC can handle complex trajectory optimization problems, and this is essentially a direct optimization approach. And some of the features can be highlighted as marginal sensitivity to the initial guess because of the architecture of this algorithm that I am to explain it later. And solving the system dynamics analytically, which is featured by handling bank singular structures, leading to a sparse nonlinear programming, and CMP complete. CMP is a lemma, or I better say it is a conjecture that asserts each direct solution will eventually converge to an indirect counterpart solution, and this correspondence or equivalence known as covector mapping principle, contracted as CMP. And CMP complete means that this map preserves the order. So there is an order preserving map between dualization and discretization. So we can say it is CMP complete. So PADOC is based upon two techniques or two sub-methods. One of them is average nonlinear programming that we have proposed it in PADOC paper, and the other is segmented atomic decomposition method, which is a nodal version of the former decomposition method that circumvents the hurdle of convergence without any issue, and it is suitable for any types of nonlinearities. So SADM works as dividing the domain into some subdomains, and then by using the principle of perturbation, which is linked to an inverse linear operator in each subdomain, we can analytically solve the nonlinearity. And here the A denotes the Adamian term, which can be computed in this way after a proof. So SADM guarantees that the solution for the system dynamics are always analytic. And this ANLP, average nonlinear programming, can be explained through considering two problems, problem 1 and problem 2. Problem 1 is to generate a distributed control, and problem 2 is to generate staircase solutions. And the ANLP theorem asserts that if the minimum of the problem 1 is equal to the minimum of the problem 2, therefore this should hold also for the multipliers. And the ANLP conjecture is that the convexity or the non-convexity, or better say all the information of higher dimensions, which is related to P1, can be transferred to the lower dimensions. So by understanding the structure of lower dimension, we can simply identify the structure of the higher dimensions. So here, accounting the ANLP theorem, PADOC generates staircase solutions and transforms them to the distributed ones by the help of Hamiltonian. So the features can be regarded as mitigating the chattering response over the singular extremals by altering the projected Hessian matrix. And for non-bang or non-singular problems, ANLP detects the optimal solution immediately. And for bang singular problems, ANLP detects the optimal structure immediately. ANLP provides reliable initial guess, and of course it avoids falling into the possible local optima. So this is an example of a Van der Pol oscillator problem. So with ANLP, we imagine that the control is defined only over one segment. So after the solution, here is the solution, the optimal control for the problem. But it has nothing to do with the actual control behind the solution of the PMP equations. But after using the Hamiltonian function, this solution, the red one, can be transformed into the red one in here, which immediately gives us a trace of the actual solution behind the optimal control problem. And when we increase the order of ANLP, the solution converges drastically to the actual one. So we only need to just calculate or compute the first few terms of ANLP and then convert them by Hamiltonian to the distributed forms with very good graphic visuals. So this is another example of a minimum fuel cruise flight, which is a singular problem. So we started this nonlinear programming with fixed and very bad initial guesses with an Euler-based transcription method. And here are the two responses from the full simulation and the ANLP response. The full simulation is filled with the chattering and fluctuations, and we cannot detect the singular structure behind that, but with the ANLP we can simply figure out the structure of the optimal control. And when we use this result in the Hamiltonian to just form the switching function, we see that the switching function is almost uniformly zero. So it tells us that the whole region is covered by the singular extremal, and there is no bank region, of course, because of this behavior of the switching function caused by this ANLP solution. So this is another example of hang glider, which is a non-singular example, but it is an intermediate problem in terms of complexity. So the solution, the actual solution, the distributed solution, which is the which is the black line, has been obtained by Paduk after 26 seconds. But this ANLP solution, with almost the same objective functional, in less than 1 second, with the same accuracy. Okay, and this is another problem. Which is the alley problem. The problem, again, the NLP here shows its performance moving from M1 to M4, and the optimal structure will be immediately detected. So the last algorithm here is linked to a paper that that it is in its last stage before submission. It is almost ready, but it needs some more review. So we call it IPSA, Indirect Bank Singular Algorithm. We again just omit the mathematics behind this algorithm, but it applies ANLP to detect the optimal structure, and then it exploits a Pontryagin maximum principle and computes the global singular extremal in terms of Jacobian composition, which is linked to the Lie bracket notation in mathematics. And then it solves the coastate system from the edges of the singular extremal by backward and forward integration. And eventually we will have a shooting system that can be also viewed as a very, very sparse nonlinear programming. But here in this paper, we have used an somewhat altered version of IPSA. The steps are quite similar, except for the step 1, that here we use an iterative search to search through the different permutations and to find the optimal structure. So, okay, and this is some results from the IPSA and how it works for different scenarios, considering some storm-like wind profiles, and the algorithm is stable. The future works is to continue working with the algorithms that we have already proposed and to eventually solve the full 3D ATO by IPSA and compare it with Paduk. Thank you for your attention.